Hello geometry students, and welcome to a video on graph theory. This is the fourth and last kind of geometry that we're going to study. And just to remind you, the other three are: one is coordinate geometry. Oops. Number two is synthetic. Number three is discrete. And now we're on number four, which is graph theory. So what is graph theory about? Graph theory is about networks. It's a little different than the other geometries, because in graph theory, a point is not the way you think of points in other geometries. It's not about whether it has size or not. It doesn't really have size because it's not like a dot. It's not like that at all. It's actually what we call a node. Okay? And a line is an arc that connects two nodes, or possibly even a node to itself. So it's an arc that connects two nodes. So for example, this is a node and this is a node. A line would be something like that. Oops, got to connect it. And the interesting thing about graph theory that makes it different from other geometries is that you can have several lines go to the same node. You can have 3 lines, 4 lines. So more than one line can go to any 2 nodes. That's a pretty important difference, because you can't do that in any other kind of geometry. You can't have 2 points. And if you're talking about straight lines, because every other geometry lines are considered to be straight, but in this geometry, these lines are arcs. They can be curved, so there can be many, but there can only ever be one line going through 2 points in every other geometry. And by the way, this is a little hard to read, but this is an N. Okay. So these diagrams, they're networks. Okay, these are 3 different networks. And what we're going to try to do is we're going to try to see if we can trace a network by starting at one point, any point that you want, and then tracing your path, just like it says in the directions here, without lifting your pencil and without retracing at all. So you're trying to just get from one point and then back to that same point without lifting your pencil and without retracing. So I'm going to pause it, and I'm going to let you think about that for a minute and see if you can determine whether or not any of these paths are traversable. Now, if you can do this, it's called a traversable path. So that's what the word traversable means, and that's going to be an important concept for this kind of geometry. Okay, I'm going to give you a minute to try it out, see if you can figure it out. Okay, hopefully you tried to trace these. Another way to do it, if you don't want to trace it, if you didn't print this out for any reason, then you could just try to redraw it. Just redraw it without ever drawing any line twice. Okay, so how can we tell if a network is traversable? How can we tell? So there's basically 2 ways. One of them is you can just try it, and if you succeed, you succeed, and then you can tell. But another way is to follow this method that I'm going to guide you through, and it's just a few steps here. Okay, so we're going to count the lines going through each node. All right, so there's a node here, A, and there's 1, 2, 3. I'm just going to put a 3 there. There's a B here and also has 3. C also has 3. Oops. D also has 3, and there's also one here, and that has 4. Right? 1, 2, 3, 4 going into that one. Okay, it doesn't matter if it goes through it. It's just from each direction we count that. So even if you have a node like this and you have something like that going into 2 places, that's like 1, 2, or like 1, 2 for that point. Okay, so let's do that for the others. So I'm going to pause it and let you try to fill those out, and then I'm going to tell you how many there are for each one. Okay, so there they are. The first one has all 3s and 1 4. The second one has 2 3s and 4 and a 2. And then the third one has 4 4s and 2 2s. Okay, so what does that mean? So that step is done. Now the next thing is to look at each number, and all you have to do is determine whether it's even or odd. So this node over here is an odd node. This is a 3, so these are all odd nodes on this one. Here we have 2 odd nodes and an even, and an even node. And this one has all even nodes. Okay, so once you've determined that, you just have to look, and the rule is if a network has 2 or more odd nodes, it's not traversable. So the first graph, graph 1, is non-traversable. The second graph has exactly 2, so that is a traversable, and also graph 3. So graph 2 and 3 are traversable. Now part of the fun here is who figured this out, and I'll tell you why it's fun, because it's this guy right here. And I don't know if you know how to pronounce that, but that sounds like so Euler is the guy that figured it out. You guys are all Eulers, so you have math in your blood. All right, here's a fun problem that really, this is what started it all. All of network theory started out with the famous Konigsberg bridge problem, which dates back to the 1700s. And basically this is just a map, and each one of these little things right here, these are all bridges. And there's 7 of them altogether in Konigsberg. Okay, there's 7 bridges. And what the people of Konigsberg used to do was they would walk through the city and walk across these bridges and sort of make a game out of it and try to figure out if they could walk over all of the bridges without going over any bridge twice. So they basically were asking themselves, before they even had the language for it, is this bridge traversable? Is this network of bridges traversable? And so we're going to figure out the answer to that question using Euler's rule that we found here in steps A, B, and C. So the first thing we have to do is we have to recognize that when we're looking at these 7 bridges, we can draw this as a network. Now remember that the nodes in graph theory, it's not about the size of the points, it doesn't really matter. So this big A here, this is all one giant point. And this is another point right here. And here, this whole area of B, that's another point. And then up here with C, that whole thing is another, actually extends all the way over here. That whole land area is another point. So what we've really got here, I'm going to try to draw this as a network, is we've got the 1, 2, 3, 4 points. So I'm going to put B on the bottom. A, this is B, this is A, this is C, and this is D over here. And let's see if we can draw now the bridges that connect those points. So between A and B, there's this bridge and this bridge. So I'm going to just put the 2 lines, as they're called in graph theory, there, okay? Between A and C, there's also 2 bridges. So let's put 2 bridges there. 1, 2. Let's see, that takes care of 4 of our bridges. There's one bridge that connects A to D, so let's draw that one. And then there's a bridge here that connects B to D, so let's draw that one. And then there's one more bridge here that connects C to D, so let's draw that one. So there's the network. Now all we have to do is figure out whether this network is traversable. So let's, again, pause the video, see if you can figure out how many lines are at each node. There's only 4 nodes here, and then determine whether it's traversable or not. Okay, I'm going to pause it, and I'm going to write in the number of lines at each node. Okay, so all of the nodes in this network are odd. and there's more than two of them. So therefore we know by Euler's law that this network is not traversable. It's probably why this question remained for so long, because once somebody did it, they'd say, oh, just follow me, I got it. But nobody ever did that because it was not traversable. So there's 4 odd nodes, more than 2, which means it is not traversable. Okay, that's it for graph theory, and that's it for the 4 geometries. I hope you found this video helpful.